Hello everybody, this is a question about advanced SHM, sounds like an oxymoron, advanced simple harmonic motion, and it's specifically for HL students for the HL content of topic C1. Here we go. So the point of the question is to show that the expression for change in height of a pendulum as it goes from the equilibrium position to its maximum amplitude is equal to that equation 0.5 times omega squared times x squared times divided by g. And we're not talking x naught, the maximum amplitude. We're in fact talking some other amplitude somewhere along the ways, okay? And because there's a change in height, there's a bit of a hint that it's something to do with energy. So what you have to do is come up with a way of showing that this equation is equal to the change in height of a pendulum. Okay, so pause the video, give it a little shot and see how you get on. Otherwise, here we go. So we're looking for the change in height of the pendulum between equilibrium position and whatever x displacement it may be. So the red equation in the bottom left must be equal to delta H. Now it's primarily to do with energy, and although it's not given in the formula booklet, there is a way of working out the kinetic energy of a pendulum by taking the equation for kinetic energy and combining it with this equation for velocity for simple harmonic motion. The square roots generally give people a little bit of fear, but if we square that entire equation, we can actually figure out a way of getting towards x. So if we square the equation and v squared is equal to omega squared, and then the stuff in brackets, we can substitute that into the kinetic energy equation to give us that third equation at the bottom there. And that's going to help us a lot in a minute. Anyhow, that's how we get towards x and sort of tie it to concepts of energy. Next up, we have to realize that the total energy is always going to be a combination of the kinetic energy and the potential energy, sort of interchanging between each other in a pendulum. When the kinetic energy is a maximum, the potential energy would be at a minimum and vice versa. And we actually now have expressions for all of these. We can take the equation in the formula booklet for total energy. We've just derived a new equation for kinetic energy. And then potential energy in terms of the change in height would simply be given as mg delta h, which you did in Unit A. And if we can solve this expression here, then we can figure out delta h and see if that red equation is equal. So what we do, you'll notice that for the green equation, I've moved it for the left hand side of the equal sign. I've also multiplied out the brackets. And what you can see is that the first two expressions are both the same and one is minus. So they'll both actually cancel. At half m omega squared x naught squared will cancel, just leaving us with another equation which also has masses that can cancel. This leaves us with this term, and you can kind of see where this is going. If we move g over to the other side, then the loss in kinetic energy is going to be used to buy height and the pendulum as it swings upwards. This actually takes us to, if we change the fraction into decimal, that gives us our final answer, and we're done. There you go.